Okay, in this video I'm going to talk about doing the weak base calculation, and I'm going to find the pH of a weak base with some given concentration. So just for the sake of a question, let's say we have 0.1 molar solution of ammonia, so ammonia NH3. We can write out the acid-base reaction for this, plus water, liquid, and that's going to form an equilibrium, donating it or accepting a proton from water to become ammonium, and as a result increasing the hydroxide population. Now we have 0.1 molar NH3, and this is in our initial condition. We're not going to include this column because it's a liquid, and we have zero concentration of both of these. So we're going to change to produce these two species and reduce this species, and they're all 1-to-1 ratios. And then at equilibrium, we'll have 0.1 minus x over here, x and x. I'm going to see if I can use the 100 rule to simplify this. So the concentration of my reactant divided by K is 0.1 molar divided by 1.8 times 10 to the negative 5. Which works out to 5,555, which is bigger than 100. So the 100 rule should be okay. We'll do it, and we'll do usual looking at it at the end to make sure that it made sense. So what that means then is that x is small, which means 0.1 minus x is going to be approximately equal to 0.1. Now my Kb expression here has the concentration of my ammonium ion times the concentration of the hydroxide that's being created divided by my initial concentration of ammonia. So what was my K? 1.8 times 10 to the negative 5. This is x, so that's going to become x squared on the top. And this is 0.1. Again, I'm only using 0.1, not 0.1 minus x, because I met my condition for my 100 rule. So 1.8, bring this up, it'll be 1.8 times 10 to the negative 6. And this is going to be x squared, so I can square root both of these. And I get 0.00134. So remember, my initial assumption here was that 0.1 minus x should be approximately equal to x. So 0.1 minus that works out to 0.0986, and that's really close to 0.1. Sorry, that should be approximately equal to 0.1. So that's really close, so the approximation is very good in this condition, which means this prediction for the change is a very good prediction. So now to do pH, I'm interested in my hydroxide population first. Hydroxide population is just equal to x, so that will be equal to 0.00134 as a concentration. I can't calculate my pH directly. When I have a base, I have to calculate my pOH, which will be negative log my concentration of hydroxide. Which works out to 2.87. And then I recognize that my pH and my pOH, I showed you this formula in a previous video, but I didn't explain where it came from. A couple videos from now I will derive this expression that relates pH and pOH. So if you work ahead, you will be able to find a video where I show you why this is the case. At any rate, pH plus 2.87 will equal 14. So my pH works out to be 11.1 for my base, which makes sense because bases should have pHs that are over 7. So that's how I can do an equilibrium calculation to determine the pH of a weak base.